All right, guys. This video I just made real quick for the students who were on that band trip or orchestra trip, the one to Chicago that missed today's class. Today was kind of our last lesson on the initial part of Unit 6, so we're finishing up all of our instructional stuff on the thermodynamic side of Unit 6, which is the new part of it is the delta G and the delta S and bringing delta H, which we've learned a lot about back in Unit 3, bringing that back into play and kind of connecting all three of them. Okay. And and then throwing temperature into the mix as well. So um, after this, in class, we're not going to do any more instruction regarding the first part of Unit 6. So that's concept check 1, and that's the Schoology assessment 6.1 and 6.2. Okay. So um, after you go through this, you should be working on those if you haven't done them already. Some of you have already done them because they were already due. Okay. But now they're going to be kind of officially due. Next class, we're moving on to electro, the second part of Unit 6. So that's 6.3, 6.4, and 6.5. And we've already talked a little bit about electro, so you can start working on concept check 2 and the 6.3, 6.4 assessment. You might not be able to answer all of them, but you can work on some of them. Okay. And on next class, we will be kind of getting back into the normal structure of the class where we get guided notes and all that stuff. Okay. But that's going to be focusing on the electrochemistry part of Unit 6. Okay. So, kind of like we did last week, we took a bunch of free response questions released from College Board to see how they ask Unit 6 stuff on there. We're doing the same thing, but we're doing it with multiple choice. Okay. The main focus is going to be the unit, the thermo stuff, delta G, delta H, delta S, all that stuff. But there's going to be a couple electro questions, but the concepts we've already talked about. And then also a couple of the questions tie thermodynamics in with kinetics, and kinetics is our Unit 7. But they're pretty simple concepts, so I'm going to introduce those in today's lesson as well. Okay. But we're doing today's lesson using multiple choice questions from previous AP exams. Okay. Just so we get used to, what do they give us on the AP exam, all the different conclusions I can jump to, how to eliminate answer choices and that kind of thing. Okay. So if you're not 100% sure, maybe you can cancel out 2 of the answers because they're incorrect, and then you take a 1 in 4 chance to a 1 in 2 chance. Okay. And our goal, hopefully we get everything right, but if we don't, we want to eliminate mistakes because we didn't read the question properly. And we want to make sure we're moving fast. We're not getting hung up too long on one question, all that good stuff. Okay. So we're starting with 25, but we can see as we look at the test, questions 22 through 25 here reference this material here. Okay. So, and what we're going to find out is we really need to have answered 23 to really know what we're doing in 25. Okay. But the first thing I want us to do here is just kind of jump to some conclusions based on what we're given. All right. We have a reaction that reaches an equilibrium, right? That's what the double arrow is telling me. Okay. So something with a double arrow, okay, with equilibrium constant, like that value, that's probably going to be a reaction that is reversible. It's not always favored. It's not always not favored. It's going to be reversible. And that's kind of what that double arrow is telling me. Okay. And the value of the equilibrium constant. Okay. So that's number 1. Number 2, at 70 degrees, the equilibrium constant, it doesn't matter that it's Kp. It's the equilibrium constant. It could be Kc or Kp. It doesn't matter. It's greater than 1. So that's telling me right now at 70 degrees Celsius, this reaction is thermodynamically favored. It would mean that at this temperature, delta G is negative. It would mean at this temperature, if they brought up cell potential, which they probably wouldn't for this reaction, but if they brought up cell potential, it would have to be positive, all because we're told at 70 degrees at this temperature, the equilibrium constant is greater than 1. Right now, at that temperature, the reaction is thermodynamically favored. And we know the sign of delta G right now at 70 degrees. We know the sign of cell potential. Okay. Another thing we need to start getting used to and jumping right to it, okay, is being able to look at the equation and predicting the sign of delta S. We have 1 mole of gas to 2 moles of gas. So now I know delta S is positive. Okay. That's good. All right. And then another thing to think about, if delta S is positive and delta H is negative, the reaction's always thermodynamically favored, right? No matter what the temperature, okay? But this is a reversible reaction, and the equilibrium constant isn't that big. It is greater than 1, so it's favored, but it's not that big. So it's probably a reversible process. So that means if delta S has to be positive, then that must mean this reaction is endothermic and delta H is positive. Because if you have a positive delta H, positive delta S, you're sometimes favored, okay? You're favored as temperature increases for endothermic, and you're favored as decreases if it was exothermic, okay? So we're pretty sure that it's an endothermic process because delta S is positive and the reaction's not always favored. So that means delta H also is positive, okay? So these are all connections you can make before you even read the questions just by this information. So let's see what we have on the notes here, okay? All right, so we're told at 70 degrees, the equilibrium constant is greater than 1, delta G is negative, okay? 1 mole of gas to 2 moles of gas, we know delta S is positive, okay? But here is where we really confirm that delta H is also positive. They tell us that when we put the equilibrium mixture into an ice bath, so when we lower the temperature, it favors the reverse reaction. Now, they don't say that exactly. We have to understand how this would look, right? You have a colorless gas and then you have a brown gas. If you have more of the brown gas, you're going to be more brown. If you have more of the colorless, you're going to be light brown and more colorless, right? So it said as we decrease the temperature, as we put it in an ice bath, the equilibrium mixture turned a lighter color, a lighter shade of brown. So the removal of heat shifted the reaction to the left towards colorless. All right. That means heat is a reactant because the removal of heat shifted it towards where heat would be. The removal of heat shifts it where heat is. That's to the left. That's to the reactants, positive delta S. Okay, endothermic. So from number 23, we determined the forward reaction is endothermic. Okay. So now we know it's endothermic. So if we go to number 25, it's saying what's true about the delta H? Well, we know we can cancel out choice A and choice B because they're saying delta H is negative, less than 0. Okay. Well, we know it's got to be C or D because we know delta H is positive. It's greater than 0. Okay. And then which one of these is a true statement? Okay. Delta H is positive because energy is released when N-N bond breaks. No, breaking bonds absorbs energy. So obviously the answer is D. Okay. All right, let's move on to another one. Okay. So here is more of an electrochemistry question. Okay. So not thermodynamics. Okay. But they bring in delta G into it. So there's thermo, and it's connecting thermo and electro. Okay. We can't eliminate things off the top of the bat. We know whenever cell potential is positive, delta G is negative. So we have no contradictions here. So we can't cancel any of these out. Okay. Now remember what we do. We're always just going to be given reduction potentials, and we got to know we're going to have to reverse one of these reactions to make an oxidation reaction. Okay, which one do you reverse? Well, if you want a galvanic cell, a battery, you want a spontaneous redox reaction, you need a positive cell potential. So which one do you reverse and flip the sign? The lowest one. So we're going to reverse this. Manganese is going to be oxidized, and the chromium ions are going to be reduced. That makes this a positive. And then positive 2.37 plus negative 0.74 equals positive 1.63. So now we can eliminate C and D. So the question is, we know the right value of the cell potential, but how do we figure out the value of delta G? Okay. Well, if we weren't sure, well, we just made it a 25% chance of getting it right to a 50% chance of getting it right if we have to guess. Okay. But there's an equation. It's on your formula sheet. You've seen it. And it ties delta G, thermodynamics, with cell potential, electrochemistry. And that's this equation here. Delta G equals negative NF cell potential. It's on your formula sheet. F is a constant. It's on your formula sheet. It's equal to 96,485. Cell potential is cell potential. We just calculated it. It's 1.63. The only thing we need to figure out is what is this N value. Remember, N usually means moles of something. And in this equation, anytime it's an electrochemistry equation and it has N in it, it's moles of electrons. But this is where we got to be careful. We got to get the moles of electrons that are transferred from the oxidation half reaction to the reduction half reaction when it's balanced, when the electrons would totally cancel out. So where did 6 moles of electrons come from? If we go back up to here, okay, this half reaction has 2 electrons. This one has 3 electrons. So I got to double this equation. I got to triple this equation to get 6 electrons. And I got to double this equation to get 6 electrons. So that's where that 6 moles of electrons transferred comes from. And that's what I plug in here. Now, when you plug in those numbers, you get negative 944,000. Okay. But if you look at the answer choices, it's negative 944. Okay. What's the deal? All right. Whenever you use this equation, when you solve for delta G, your answer is in joules. But notice they wanted the answer in kilojoules. So all we had to do was divide this by 1,000 to make it kilojoules. And that's where we get choice B from. Okay. So cell potential has to be positive for a spontaneous oxidation reduction reaction. And just remember, cell potential is weird in terms of kind of like Hess's law, right? If you reverse a reaction, you change the sign of the potential. Okay, so if it was negative, it becomes positive. But remember, if you double or triple or whatever to a reaction, you don't change this value. So it's still, this is the right value here, but we needed to know 6 moles of electrons transferred to get that value. And you have a calculator while you're taking the AP exam, you can plug it in, you get that number. Wait a minute, it's negative 9. It came out to be like negative 9,438. So it rounds up to negative 944 for 3 significant digits. Okay. But it was just kilojoules versus joules. Okay. All right. So let's go to the next one. All right. So we've talked about this question a lot throughout the year, but only in terms of delta H. Okay. We should understand that breaking solvent-solvent attractions, breaking solute-solute attractions. What are we breaking? The hydrogen bonding in the water in this case. We're breaking the ionic bond here. Axing is taxing. So we know that the delta H for this should be positive. The delta H of that should be positive. Breaking bonds requires energy. Okay. And then we should understand here, they're not drawn, but we have ion dipole interactions occurring between those ions. And those are the new attractions that are formed. So that releases energy. So that process should have a negative delta H. Okay. So we can eliminate choice C and choice D because choice C and choice D has negative, negative, positive for delta H. It has negative, negative, positive for delta H. And we know it should be positive, positive, negative. So choice A and choice B are guesses, right? We've eliminated C and D. So the question is, does entropy increase or decrease? Does entropy increase or decrease? Does entropy increase or decrease? Okay, for each step. We know what happens to enthalpy, but what happens to entropy? Okay, well, if you loosen up particles, they get more disorder. So loosening up the particles, positive delta S, positive delta S. The problem is, right, both those have the right choices. Okay. Now the question is that increasing entropy or decreasing entropy? And it's not about the overall change. Overall, a salt dissolving in water increases the entropy of everything. All right. Overall, the overall process is going to be a positive delta S. But this process in particular, you have loose ions, you have loose solvent particles, and now they're arranging themselves so they're attracted to each other. And the picture kind of gives you an idea. It's getting more ordered. So just this part, the ions arranging themselves around the water and the water arranging itself around the ions in the most stable way, meaning introducing the most attractive forces possible, that brings the entropy down. So that part would be a negative delta S. So the answer ends up being A. Okay. All right. All right. All right. So this one, there's a lot going on in this one. Okay. 39 should be an easy one to answer from unit 4. Okay. If you don't know how to do it, you should definitely ask before the AP exam, before the final exam, because that's an easy one. Okay. Now, these two, you're going to find out we should be able to answer very quickly once we make all of our assumptions of the stuff that we're given. This one's a little bit more time consuming, but it's easy to do. It's just going to take a little bit more time. So, you have to make those risk reward assessments. I know how to do this one, maybe after I've kind of broken down the problem. I get how to do it. I just don't want to put in the time in right now. I'm going to start it. I'm going to come back to it. I'm going to flag it, electronically and come back to it if I have time. And if I don't have time, I'll just take a guess at that point. Okay. Right. So that's kind of the way, you should be thinking about it in terms of time. All right. Now, this is the reaction. This is the thermodynamic data for that reaction. So what do we know? We know it's endothermic, right? Positive delta H. Okay. We know it decreases in entropy, negative delta S. Okay. And we know right now at the temperature, the reaction's not thermodynamically favored because you have a positive delta G. So that means at this temperature, and it's 298, that's what that little subscript is, like the delta G at 298, right? That means at 298, the equilibrium constant is less than 1, okay? It means the cell potential, they probably wouldn't ask about cell potential for this reaction, but the cell potential is negative because the delta G is positive, right? Does that make sense? Okay. And as soon as we made that judgment, we can answer number 38. It's B, right? The equilibrium constant is always greater than 0, right? You never have a negative equilibrium constant. It's just, right, usually it's in scientific notation. Do you have a negative exponent in your scientific notation or a positive? Is it greater than 1 or is it less than 1, right? That's really what you're looking for, okay? And we know it's less than 1 because delta G is positive, okay? And there's the equation on your formula sheet that if you have the delta G, you could calculate the equilibrium constant, okay? And you can use that equation, but we just know it's less than 1. So we answered that question, okay? Now, another conclusion that should spring to your mind as soon as you see this combination, positive delta H, negative delta S, is the reaction's never favored no matter what the temperature. So that answers this question. Number 36. It's not favored at any temperature. That's what those signs tell me. Not the values, the signs. Positive delta H, negative delta S. Doesn't matter what temperature I plug in. If I plug into that equation, delta G equals delta H minus T delta S, no matter what number I plug in for temperature, delta G is always going to come out to be positive. So this reaction is never thermodynamically favored. Okay? So let's see if we have those notes, right? So again, KQ is less than 1. We got that answer. And then again, that combination never favored. Okay. If it was positive, we know it is more favored. It becomes favored at higher as temperature increases. If it was negative, it becomes favored as temperature decreases, right? All that stuff. But positive delta H, negative delta S, never favored. Okay. Now, this one, we have to go back to unit 3, right? This is straight up delta H question. How do you calculate the delta H of reaction? Well, we already have it calculated for us. We know what the delta H is, but one way to calculate the delta H of reaction is using bond energies, and that's what we're given. But this is where we have to be careful, right? Every time you look at your formula sheet, it says delta H of reaction, products minus reactants, delta S of reaction, products minus reactants, delta G of reaction, products minus reactants. Okay. You're always thinking products minus reactants, final minus initial. And that's what you should think. But you have to remember for bond energies, it's reactants minus products, bonds broken minus bonds formed. And that equation is not on your formula sheet. You got to remember it. Okay. The other way to do it is if you always want to do products minus reactants, is you have to make the bonds of the products negative bond energies, because bond energies are always given to you in the amount of energy to break one mole of the bonds. But the bonds of the products aren't being broken, they're being formed. So you have to make it a negative energy value because energy is released when that bond is formed as a product. It's broken when that bond is broken as a reactant, but it's released when that bond is formed as a product. Okay. So if you want to do products minus reactants, then you got to know which bond energies that are the products bonds and make them negative. Okay. If you don't, then you got to do bonds broken minus bonds formed. Now, they gave it to us. So notice they didn't give us all the bond energies. They didn't give us the carbon-carbon double bond. They didn't give us the carbon hydrogen bond, but we don't need it because those bonds aren't broken and those bonds aren't formed again, right? That bond never broke. It's here and then it's here, okay? So we have to look at this and see what bonds were broken and what bonds were formed, okay? So what bonds were broken? Well, this CO bond is broken, right? You don't have it over here anymore, okay? This NH bond is broken. You don't have it over here anymore. So the bonds that are breaking are CO and NH, okay? So I'm going to say my delta H, which is positive 12, equals bonds broken. The NH bond was broken. That's where the 390 comes from. The CO bond was broken. That's where the 360 comes from. Bonds broken minus bonds formed. Now, one of the bonds that is formed is the unknown, the one we're solving for, right? That's the CN bond that wasn't given. But notice that we have that new bond, right? They pointed out. That C is not bonded to that N, but now it is. So that is a new bond formed, and that's the one we're calculating the energy for. So that's my unknown. The other bond that's formed, might be a little bit more difficult to see. But so the bond between C and O is being broken, but you're replacing it with the H over here. So the OH that comes off of this is going to bond with this H coming off of this, and that's where the water comes from. Now be careful. What if they asked you the shape of the water? A lot of students would say linear, and we all know it's bent. So don't fall for that, okay? But they didn't ask us that, okay? So we know that the OH bond was formed, so that's one of the bonds over here, and the other one is what we're solving for. So 12 equals this minus this, and we're solving for X. When we solve for X, it comes out to be, I think, 278 if you calculate it, and the closest answer would be 300, okay? All right. Whoops. All right. Okay, here. All right. I didn't circle 42, but we're going to answer that one as well. Okay. But we're given this. Now, we'll talk about what slow, fast means and all that stuff. What we need to recognize here is if we add these equations up, we get that equation. So all we have to do is add these up to get the delta H of this overall reaction. Okay, pretty easy. So notice that's what I did here. I added them up. So I know the delta H of this reaction is negative 186 for that reaction there. Okay. Another thing that we need to, other thing we need to make a note of is the value of the equilibrium constant. This should scream to you the reaction is extremely favored. Delta G would be extremely negative. Cell potential would be extremely positive. Okay. But the interpretation you should make about an equilibrium constant like this is this reaction goes to completion. This reaction goes to completion. This double arrow is kind of a distractor. The reaction pretty much goes to completion. So if they asked you an equilibrium question where you're making a rice chart and all that stuff and trying to figure out, the final concentration of something, don't treat it like an equilibrium. Don't make a rice chart. It's a limiting reactant stoichiometry. The reaction stops when you run out of one of your reactants. Okay. Now, the reason why I do want to answer number 42 is essentially number 42 is just asking why So why it's asking, why is the equilibrium constant so big? You need to interpret that is that means the reaction is very thermodynamically favored. And so what's driving the favorability? If you're asked what's driving the favorability, it's either delta H or it's delta S. Delta H can only drive the favorability if it's negative. Delta S can only drive the favorability if delta S is positive. Okay. Now it's hard to find, it's hard to predict the delta S for this reaction because we have two gas molecules to two gas molecules. So delta S might be slightly negative, it might be slightly positive. We know it's not that big of a change. 2 moles of gas to 2 moles of gas, we're not, the entropy isn't changing much. So whatever the entropy value is, negative or positive, we don't have enough information really to make that call. It's a small value, whether it's negative or positive. Okay, so it's not the entropy change being very positive that's making this reaction thermodynamically favored. It's the fact that it's incredibly exothermic. Okay, so the answer to this question, is the delta H being so negative is what's driving it. Okay, all right. If choice C, if we had a delta S that was very big and positive, that could be an answer. Okay, but we know delta S is going to be a small value because there's not a big difference in entropy on either side. So entropy change, even if it's positive, isn't going to be the driver of favorability. It's going to be the fact that it's very exothermic. Okay, and this one we got to be careful, right? Remember, we added up the delta H for this reaction, and this shows the formation of HCl, and so a lot of kids are going to pick that one. But this is asking for the enthalpy change per mole of HCl, but this shows 2 moles. So what did we do? We had to divide the delta H by 2 to get the delta H for 1 mole of HCl being formed. So that's why it's A. Okay. All right. Moving on. Okay. So this one ties in unit 7 with thermodynamics. So essentially, the way you should read this question is the reaction happens, once the reaction starts, it happens vigorously. So that's telling you have an endothermic process, or not an endothermic process. It tells you you have a thermodynamically favored process. It could be exothermic, it could be endothermic, sorry. Okay. So it's a favorable reaction at this temperature, but the problem is when you mix the two reactants, the reaction doesn't happen. So you're going to see this probably once or twice on the AP exam. A reaction is thermodynamically favored, but it's not happening. Okay. Kind of like combustion reactions. Combustion reactions are always favored, but just because propane's leaking out of the container and there's oxygen in the atmosphere, it doesn't mean the propane's going to burn, right? What do you need? You need a spark. Okay. You need a spark. What does the spark provide? It provides the activation energy. So whenever you're given this kind of scenario where you have a reaction, you're told it's thermodynamically favored in some way. The reaction happens vigorously. That's telling you the reaction happens, okay? It just needs to get triggered, okay? Well, that trigger is the spark. It's the thing that starts the reaction. And then once it's started, it's self-sustaining, okay? But it needs that activation energy. So whenever you have a reaction that's thermodynamically favored, but it's not happening, it's probably because it has a high activation energy. So we're looking for that answer, and I think it's answer D, the reaction has a large activation energy. It's supposed to happen. Thermodynamics tell me it's favorable, but it's not happening, and that's because the collisions are happening, but they're not happening with enough energy to overcome the activation energy. But once one collision does, then it keeps going, okay? So that's choice D, okay? All right, so number 50, we have an exothermic process represented above, can be classified as, this was just a review of, do you know the difference between chemical change and physical change? And obviously this is a chemical change because we're forming new substances, right? If this were just H2O liquid yields H2O gas, that's a physical change. If it was salt solid yields aqueous ions, salt dissolving, that's a physical change, right? But we're breaking covalent bonds and we're forming new covalent bonds. So this is a chemical change. So we can eliminate A and B, okay? And the fact that it's exothermic just means we're breaking some bonds, we're forming new bonds. The bonds that are formed are stronger than the bonds that are broken, that kind of thing. But it's a chemical change, okay? The fact that it's exothermic really doesn't tell us much about the entropy change, okay? But if it is exothermic, we can look at the entropy change. The entropy change is going to be positive. So this would be one of those reactions that's always favorable, a negative delta H exothermic, and we're increasing the entropy because we're getting that gas. So positive delta S. Okay. All right. Oops, wrong thing. What am I doing? What did I say? Oh yeah. Let's see. Did I say any notes? No. All right. All right, let's go to the next one. All right, so this one was like the first multiple choice question on a test a while ago. And it's really easy. It's just which of these equations would have a negative delta S, so decreasing in entropy, and it would be D, right? Gas to liquid. Everything else would be a positive delta S. Okay, so real easy one there. Okay. Okay, here we've probably seen this one before, maybe on a concept check or something. Okay, but we have different combustion reactions here. Notice their delta H's are all negative, so right, but it should make sense. Combustion is exothermic, right? So we got they're all exothermic, and 16 is just explain why it's exothermic. So just knowing that that means more energy was released when bonds formed than required to break the bonds. So choice D, the energy required to break the bonds and the reactants is less than the energy released when forming the bonds in the products. Okay. All right, we go to the next one. Okay. All right, so here we have this is another one of those questions is what's driving the favorability? It's a favorable reaction when we drop this salt in water, it starts to dissolve. The reaction's thermodynamically favored. They tell us that in the question, but they tell us when it dissolves, it's an overall endothermic process. So positive delta H. And so if we're asked what's driving the favorability, well, it's not delta H. That must mean it's delta S. What's favored in terms of delta S? Positive delta S. So endothermic reactions, if they're favored, it's because they have a positive entropy value. And so that would be D. Dissolving the salt increases the overall entropy. All right. And that's true. Solid salts have less entropy than aqueous salts, right? Aqueous salts are more chaotic because the ions are moving around in solution versus stuck in a solid structure. Okay. All right. And we keep on going. Oops. Yeah. So again, what's driving favorability? Remember, delta H can only drive favorability if it's negative. Delta S can only drive favorability if it's positive. Okay. All right. All right. So ignore my scribbles here. Okay. But what I wrote here is correct. So if you read the question, okay, they tell us that at temperatures below 500 Kelvin, equilibrium constant is greater than 1. Then above 500 Kelvin, the equilibrium constant is less than 1. Okay? That means, A, the reaction is not always favored. So it either is a positive delta H delta S combo, or it's a negative delta H delta S combo. Okay? Because if it was a negative delta H positive delta S, it's always favored. And this is telling us, hey, there's some temperatures, higher temperatures, where it's not favored, and there's lower temperatures where there is favored. Now that should tell us that it's this combination, okay? Because exothermic becomes favored as temperature decreases, endothermic becomes favored as temperature increases, right? So we know it's a negative delta H, negative delta S combo. Okay, so that's really what we needed to take from this. Okay. All right. All right, this one. This is another one of those ones that ties in with Unit 7. So they give us this equation, carbon diamond turning into carbon graphite. And notice the delta G. The delta G is negative. It's thermodynamically favored, okay? But it doesn't happen, right? Your diamond in your diamond ring doesn't all of a sudden turn into graphite, right? So we have a thermodynamic process that isn't happening. And I have the carbon right here in diamond form, and it's not changing into graphite. Why is that? You have a reaction, it's thermodynamically favored, but it's not happening. High activation energy. So it's the reaction must have an extremely high activation energy. And remember, back in Unit 1, we talked about the difference between a network covalent structure that's three-dimensional and tetrahedral versus the network covalent structure that graphite has that's only connected by London dispersion on the layers. So on this plane, they're connected by covalent bonds that are harder to break, but on this plane, they're stacked up on each other just by London dispersion forces. And that's why like graphite can slide off onto your paper, but diamond can't work. But again, favorable reaction, but it's not happening. You're looking for some kind of indication that you have a high activation energy. Another way you could say a reaction has a high activation energy is if the reactant bonds are really strong. So they could say the reactant bonds are really strong, and that would be the same thing as saying you have a high activation energy, because the activation energy is based on how hard the collision has to be to break the bonds that are required to be broken. Well, the stronger the bonds that have to be broken, the stronger that collision has to be, right? To activate the reaction, right? Okay. Favored but not happening. You're looking for some indication that you have a high activation energy. And again, we're going to revisit this in Unit 7, not a big deal, but pretty easy concept to think about, all right? All right, 2 more. Thanks for hanging out. Okay. Whoops. All right. So this is just Hess's law with equilibrium constant, okay? But please understand, you can cancel out these two choices, choice B and choice C, because this is impossible. You can't have a negative delta G with an equilibrium constant less than 1, and you can't have a positive delta G with an equilibrium constant greater than 1. So, you could narrow it down to a 50-50 guess. It's either A or D, right? That's one way to think about it. Okay, but you can calculate it. It doesn't take long. All we have to do is reverse this reaction here. And once we reverse this reaction, these two equations add up to this one. We just have to remember how to manipulate the equilibrium constant. We're going to keep the first reaction as is, so we keep that equilibrium constant as is. But if we reverse that equation, the new equilibrium constant for this reaction is 1 over the original. So we're going to take 1 over this really small number. Now, you should understand that 1 over this really small number is going to be a very big number when you put in your calculator, okay? So if we add them, we get our overall reaction. But remember, for equilibrium constants, we don't add them like we do with delta H's or cell potentials or whatever. We multiply them. So this times this would be our new equilibrium constant, and that comes out to be that number, 1 times 10 to the 26. So since our equilibrium constant is greater than 1, our delta G has to be negative, right? Okay. And the last one, we'll do this one quickly because, again, we're going to spend a lot of time on electrochemistry. So we really don't have to look at the picture, all right? It's a galvanic cell. They say an electrochemical cell. But what you want to see here is you have something that reads the volts, but you have no external voltage source. So it's not an electrolytic cell. So you need a spontaneous redox reaction to be occurring here. So we need to know our overall potential needs to be positive. So when I'm given my 2 reduction half reactions, which one do I flip? I always flip the lowest one. So if you have one that's positive and one that's negative, you flip the negative one and make it positive, right? If you have 2 that are positive, you would flip the lowest one, okay? Because when you flip this one, that becomes a positive, and you add them up, and we get our potential, okay? So the answer to number 11 is just going to be 0.8 plus positive 0.76, all right? All right. Now, we reverse this reaction. we keep this one reaction as is, but to add them up to get a full balanced redox reaction, we have to double this equation so that the two electrons cancel out, okay? So process of elimination for number 10, you can cross out B and C because they still have electrons in the formula. And remember, in the equation, the overall oxidation reduction equation shouldn't have electrons in it. They should completely cancel, okay? And then this one is obviously not the choice because it's saying the silver is turning into silver 2 plus, and you know, it's not. It's turning into silver 1 plus, okay? And it's not the silver. Sorry, it's not the silver that's turning into a positive ion. It's the zinc that's turning into a positive ion. So a couple reasons why that is not the right answer, but it ends up being, you know, this one. Okay, let's see if I have any notes on that one. Whoops. Yeah, so, you know, you double that one to make sure the electrons cancel, and then you would have 2 silvers plus a zinc, you'll 2 silver metals plus a zinc ion, right? Okay. All right. So hopefully that helps, especially if you weren't in class today. Finish concept check 1 for unit 6, finish the 6162 assessment. Come in ready next class, start in on electrochemistry. All right. All right.